Hurricane Lizards and Plastic Squid. In the summer of 1767, the noted English theologian, natural philosopher, and all-around polymath, Joseph Priestley, had some time on his hands. His light duties as a minister in Leeds left most of his days free, and he used that time to think, write, and tinker. Having already produced books and papers on everything from grammar to electricity, he chose as his next topic an exciting new field known then as pneumatic chemistry, the study of gases. That decision sparked what one biographer has called an intellectual streak of legendary proportions. Within a few short years, Priestley would firmly establish not only that air was measurable, but that it was complicated, a swirling mixture of distinct components. Along the way, he became the first person to isolate and describe oxygen and 10 other common gases, not to mention uncovering the basic chemistry behind photosynthesis. But it all started with his curiosity about something miners called choke damp, or more poetically, mephitic air, an invisible suffocating vapor known to gather at the bottom of coal shafts. Scottish chemist Joseph Black had recently cooked up a batch of the stuff in his laboratory by heating small pieces of chalk and limestone and trapping the fumes in a bottle. Luckily for Priestley, there was another place this gas was known to occur, and he happened to live right next door. "I was induced to make experiments," he later reminisced, "in consequence of living for some time in the neighborhood of a public brewery." There, lingering over the vats of fermenting ale, Priestley found a ready supply of the gas in question, generally about 9 inches or a foot in depth, within which any kind of substance may be very conveniently placed. Over the coming months, he placed a remarkable array of things into that bubbling zone: candles, hot fire pokers, ice, rosin, sulfur, ether, wine, butterflies, snails, mint sprigs, various flowers, and at least one large, strong frog. Perhaps the only thing more boundless than Priestley's curiosity was the patience of the brewers, who indulged their eccentric vicar even when his experiments went awry and left the beer with a peculiar taste. Like previous observers, Priestley immediately noted how the gas seemed to lack something. Candle flames were snuffed out in it, and animals left for any length of time quickly succumbed to asphyxiation. Happily, the strong frog was rescued and revived after only a few minutes. But Priestley also recognized that this mysterious vapor was more than simply an absence of normal air. It boasted unusual qualities that made it quite distinct and interesting in its own right. He learned that it would bleach the color from rose petals. He saw that it was heavy, and he watched smoke become trapped within it and stream down the sides of the vats to gather on the brewery floor. Most famously, he discovered how to quickly dissolve the gas in water, producing a fizzy beverage with a pleasant, acidulous taste. This breakthrough earned Priestley the prestigious Copley Medal from the Fellows of the Royal Society of London. It earned a lot more for entrepreneur Johann Schwepp, who copied Priestley's methods to found the tonic and soda water company that still bears his name. Thanks to such early advances, people knew quite a lot about mephitic air, including its flavor, long before chemists came up with the name carbon dioxide. Nearly 2.5 centuries after its publication, Priestley's book on gases still brims with excitement. Reading it on a blustery December morning, I found myself caught up by his enthusiasm, eager to experience those same revelations that he had at the brewery. My son, Noah, was a willing accomplice. He happened to be home from elementary school for the day, suffering from just the right sort of head cold, sick enough to miss classes, but healthy enough to enjoy some time off. "Let's find some carbon dioxide," I told him, and the game was afoot. We could have simply popped open a few soft drinks and tried to collect the bubbles. Appropriately, there were even a few bottles of Schweppes on the shelf. But somehow, relying on carbonation to get our carbon dioxide seemed a bit too much like cheating. The smoke from our blazing wood stove certainly contained the desired vapors, but how would we filter out the 60 or more other gases, chemicals, and nasty particulates? Instead, it seemed best to follow Priestley's example and go to one of the purest and most common sources of carbon dioxide on Earth: So we headed for the refrigerator. It turns out that fermentation occurs in a lot more places than vats of beer. Yogurt and cheesemakers call it culturing, but it's more accurate to think of it as a form of slow microbial digestion, a way for bacteria and other tiny organisms to extract and use energy from the foods they live within and around. Like any form of digestion, it is a process that produces waste. Luckily for food lovers, the byproducts of fermentation include things like alcohol, thus the beer, and lactic acid, which adds tanginess and pungency to such cultured favorites as kimchi and buttermilk. Most fermentation also produces carbon dioxide, which is what had me combing through the back reaches of our fridge. A container of organic sauerkraut advertised probiotic punch and claimed it's alive, but any organisms the kraut might have contained had long since shuffled off their mortal coils and were no longer producing carbon dioxide. A lit match held above the briny mix burned brightly. Experiments with yogurt and sour cream were similarly disappointing. But then we hit the jackpot. On the bottom shelf, behind the bags of carrots and celery, sat a half-gallon jar of homemade pickles. They had been stewing in their own juices since August and tasted yeasty as well as sour, suggesting that fungi had joined the bacteria in their digestive pursuits. Frankly, it was past time to throw the pickles out, but for once, procrastinating a chore had paid off. As soon as Noah and I brought a match near that open lid, the flame demonstrated why carbon dioxide is such a common ingredient in fire extinguishers. With no oxygen to burn, the match went out in an instant, as if we'd turn off a switch. What's more, smoke from the snuffed tip curled downward, trapped in the gas, just as Priestley had.
"It's pouring down the side," Noah exclaimed, watching as wisps of smoke followed the heavy vapors over the jar rim and down to spread across the countertop. "That's it," I told him. "You saw the carbon dioxide." He quickly brought me back to earth. "I didn't see the carbon dioxide, Papa. I saw the smoke." But like Priestley before us, we could use that smoke to watch the gas, defining its boundaries as it flowed and swirled around the open jar. For a few minutes, our kitchen was filled with the thrill of discovery as we lit match after match, watching them snuff and smolder until all the carbon dioxide had dissipated into the surrounding air. Simple experiments often lead to broader insights, and repeating Priestley's fermentation trick brought up an obvious question. Do pickles cause climate change? Does making beer? The answer, of course, is no. But understanding why some carbon emissions are harmless while others are not reveals a basic truth about climate change that we rarely stop to think about. In the case of our pickle jar, the carbon came from the cucumbers in the brine, and the cucumbers had gotten it from the air around our garden the previous summer. Like plants everywhere, their growth relied upon photosynthesis, that leafy process of combining carbon dioxide and water with energy from the sun to create starches. In other words, carbon dioxide puts the carbo in carbohydrates. When those starches break down, the carbon dioxide goes back into the atmosphere. This is the step in the Earth's carbon cycle with which we are most familiar, because we play a role in it every moment of every day. Whether we eat plants or eat animals that have eaten plants, the energy that fuels our body traces right back to those photosynthetic starches, and we release carbon dioxide with every exhaled breath. But in terms of climate change, breathing is like making pickles or brewing beer, guilt-free. That's because our bodies are just one short stop for carbon on its continuous circuit through the air, or from the air through plants and animals and back again to the air, with no net gain or loss. If that's all there was to the story, then the planet wouldn't be warming and I would not be giving this lecture. The reality of modern climate change hinges on one key fact: not all plants break down. Consider the pickle. Cucumbers eaten fresh or left to rot in the garden release their carbon right away. But that process slows considerably in a jar of salty brine. Under the right conditions, it can stop altogether. In nature, this occurs primarily in two locations: the ocean floor and boggy wetlands. When marine algae die in mass and sink to the seabed, they sometimes get buried before they can be eaten or decomposed. Dead plants in bogs also accumulate with little decay, building layer upon layer of peat. In either case, if sedimentary rocks form above and around those organic deposits, their carbon is effectively trapped, removed from the atmosphere, and stored there for millions of years. Transformed by heat, pressure, and age, we recognize them now as the fossil fuels. Petroleum from the algae, coal from the peat, and natural gas, which can come from either one. Burning them now returns all of that stored carbon, all that stockpile to the air at one time. It overwhelms the natural cycle and leads to all of the consequences that are now unfolding. So the lesson is, the next time you see something in the back of your fridge that looks like a scientific experiment, it is a scientific experiment. There is a lot to be learned from rotting food, and it's a good reminder that even the atmospheric aspects of climate change are rooted in biology. So we know that the climate is warming, we understand why, but what does all of that mean for plants and animals? As you can imagine, that is a booming field of study. That is a booming field of study, and climate impacts are so widespread now in nature that it's not too much of an exaggeration to say all biologists are studying climate change. Some of them just don't know it yet. So it helps to organize all of that deluge of science into themes, and one of the most common themes has to do with timing. At Walden Pond, for example, the violets and the wood sorrel that Henry David Thoreau admired in May and June now bloom by late April. And what he called that early yellow smell of willows can reliably be savored in March. Spring is arriving earlier and earlier, and you can see it happen in your own backyard. If you write your observations down, they might become valuable, as Thoreau's did. His meticulous notes on the plants and the birds at Walden are now a vital baseline for modern comparisons. One expert told me that if Thoreau was listed as a co-author on all of the papers now using his data, he would be one of the most prolific climate change scientists of the 21st century. But a modern spring isn't just earlier than what Thoreau saw, it's different. To him, it might seem like a season in disarray. And that's because not all species are responding in the same ways or even at the same times, leading to all sorts of problems with timing. There is a flower in our local flora here in the wildflower meadows that we may have all seen called the Death Camus. And like many plants, Death Camus produces toxins to ward off would-be attackers. But unlike most other plants, it doesn't just put those chemicals into its leaves and seeds and roots and places that are likely to be nibbled. It puts them everywhere, including in its nectar and its pollen. What's more, the main toxin in that mix, called zygosine, is especially nasty stuff. It attacks the heart, the lungs, and for good measure, the digestive tract. Its Latin name for the plant says it all. Toxicoscordium venenosum venenosum. Poisonous bulb, poisonous, poisonous. So Death Camus is very well protected, but in terms of pollination, it's in a bit of a bind. How do you attract insects to your flowers when instead of offering them a tasty reward, you're offering them seizures, paralysis, and, well, death? Enter the appropriately named Death Camus bee, one of only a handful of species and the only bee that has figured out a way to detoxify Death Camus poison. That gives the bee an exclusive source of pollen and nectar, and it gives the flower a dedicated pollinator. It's a very tight and specialized, co-dependent and co-evolved relationship. But in many locations, including here in the San Juan Islands, Death Camus now blooms weeks earlier than it did just 30 years ago, responding to the steady rise of temperatures in the springtime. The bee, on the other hand, nests in the ground, where temperatures are warming much more slowly. It's still on the old schedule. Now, if that trend continues, it could lead to what biologists call a timing mismatch, where the flower blooms too early for its bee and the bee emerges too late for its flower. They still overlap now, but not by much. So a timing mismatch, one of the many consequences of these changes and how creatures and plants are changing at different rates. Those specialized relationships like pollination are particularly vulnerable, but we're seeing timing mismatches in all sorts of places. Caribou herds migrating across the tundra to their calving grounds and arriving past the peak of plant productivity, past the peak of the food that they need to sustain and rear their young. Or shorebirds in migration arriving at key wetlands and missing the populations and reproduction of the invertebrates in those mudflats that they need to fuel the rest of their journey. It's happening in all sorts of intriguing ways, timing mismatches. But it can take years or even decades really for us to see and understand the repercussions of timing problems. Some climate change challenges play out much more rapidly. And we've experienced in our own backyard here the consequences of extreme weather, the droughts and the heat waves that we all experienced here over the course of the summer. We're seeing storms, there are floods, all of these extreme weather events, including just high temperatures that are beyond the comfort zone for many species. As one scientist told me when we were chatting about this, he said, sometimes it's pretty simple. Organisms just get too hot. And one such example comes to us from the deserts of the American Southwest, where you might expect creatures to be pretty well prepared for a warmer future. They live in the desert, for goodness sake. This study was done by a fellow named Barry Sinervo, who is a herpetologist at the University of California, Santa Cruz, and he studies lizards, including the western fence lizard, which is a species that if your childhood was anything like mine, you tried and failed to catch, because the fence lizards would always scamper away at the last minute underneath the rock. Well, it turns out that fence lizards use rocks for a lot more than just escaping from young lizard enthusiasts. They are what biologists call heliotherms. They use the sun to regulate their body temperature. So they bask on top of rocks to warm up, and then they cool down by going down into the shade beneath the rocks. And they can't just stay out in the sun indefinitely because their bodies cannot compensate for that heat, and they would overheat and perish in the end. So they must be close to a rock so they have a place to escape. So as the temperatures have risen, particularly in desert areas and key lizard habitats like that, the fence lizards and other lizards have responded by doing what they've always done on hot days. They spend more time in the shade. But that comes at a cost. Because any time that you are in the shade beneath a rock, you are not out foraging for food. And so as temperatures rise, the calories taken in by lizards go down. And if they spend too much time in the shade, that begins to have consequences. Barry and his team had observed fence lizard populations winking out in a number of hot sites before they finally realized it wasn't the heat killing them directly. What was happening was that the lizards were getting so few calories that particularly the female lizards could not build up enough energy reserves to reproduce. In other words, when it got too hot, the lizards stopped breeding. And it doesn't take a PhD in herpetology to predict the long-term consequences of that. So another one of these challenges created by climate change has to do with what Baloo, the bear in the Jungle Book, would have called the bare necessities of life, the simple bare necessities, so to speak. And what happens when one of those necessities disappears from your habitat? I mean, if we're talking about our polar bear example, when you lose the ice, that pack ice in the Arctic, what the polar bear loses is the place where it hunts for seals. A fundamental and vital aspect of their habitat disappearing. So that threatens the polar bears, but it also threatens another creature in that same habitat. If you could look beyond the polar bear, around the edge of the ice there, you might see a tiny little seabird called the little auk or the dovekie that feeds along the edge of the pack ice, where it's particularly rich with plankton. Well, the disappearance of that pack ice pack ice threatens those dovekies as well, because as it draws farther and farther away from the Arctic islands, like Franz Josef Land in Russia, where the dovekies breed, they have farther and farther to fly to forage for food, to take back, to feed their chicks. That distance gets longer and longer. Dovekies have long been predicted to be one of the first Arctic creatures to suffer from climate change, because there's no way they can make that round trip and keep raising chicks. It's just not going to work. The strategy will fail. But when scientists actually went up to study this in the flesh, they met with something totally surprising, which brings us to a really important point about climate change biology, and that is this: nature is not defenseless. Nature is not a passive bystander to climate change. When things change, species react. They do all they can to survive, and they sometimes do it in ways that we cannot predict. So I want to pick up that story of the dovekies straight out of the book, and it begins with a conversation with a fellow named David Gremillet, who is a French scientist who participated in a big expedition up there in Russia. And one of the things they did was study dovekey breeding colonies. We had indeed strong hypotheses and predictions on how they would behave, Gremillet explained, noting that birds in their previous studies had regularly flown over 60 miles to reach the edge of the pack ice. We were expecting flight times between the colony and the foraging spot of at least an hour, he went on. And then he recounted what he called, quote, one of the most exciting moments of my research career. Sitting with their laptops at the dinner table at the research station, surrounded by their Russian counterparts, they opened up that first batch of tracking data and saw precisely how long the birds had been in the air. Less than 4 minutes. Instead of trekking all the way to the edge of the sea ice, the dovekies had apparently found an alternative food source right on their doorstep. But what and where? It's easy to imagine the excited conjecture and conversation that came next, perhaps fortified by a sip or two of Russian vodka. Soon their ideas began coalescing around an entirely new hypothesis. My colleague, Jerome Fraught, remembered what we had seen while climbing the nearby mountain with our Russian friends. Gremillet recalled, and described a distinct line across the mouth of the fjord where cloudy blue meltwater from island glaciers slammed into the dark, dense currents of the Arctic Ocean. Both Fraught and Gremillet had trained as oceanographers before they began studying birds, so they understood exactly the consequences of such an abrupt transition. We both knew what this front meant: a curtain of plankton, killed by temperature and osmotic shock. I've never exactly quite understood what osmotic shock was, but I love the sound of it. Osmotic shock. For tiny crustaceans, swimming so suddenly from one kind of water into another was like driving full speed into a wall. And for anything that fed upon those crustaceans, the resulting pileup created a bonanza. Testing this theory, however, required a boat, and the only craft available at the research site was a, quote, chronically deflated dinghy. And the fuel that they had brought from Murmansk turned out to be contaminated with water. Nonetheless, they started this thing up, sputtered, it died, sputtered and died. They got themselves out far enough into the fjord to conduct a survey. And there wasn't much to see for the first part of that survey, but as they crossed the convergence between the glacial melt and the ocean water, suddenly the dovekies were all around them. The little auks were all there, Gremillet told me, aligned on the oceanic side, diving and stuffing themselves on plankton, easily picked from that underwater curtain. So with that revelation, the story of dovekies and climate change switched instantly from one of decline to one of resilience. Yes, the sea ice was melting as predicted, but so were Arctic glaciers. And in places like Franz Josef Land, where glaciers are plentiful, that created an opportunity that no one saw coming. Gremillet and his team spent the rest of their field season showing that dovekies weren't just surviving on their new food source, they were thriving. Chicks grew at precisely the same rate as they had on a traditional diet, measured decades earlier at the very same location. To Gremillet, the project demonstrated how one overlooked detail can have a huge effect on the outcome. Even if you think you know he summarized. You really have to get out into the field to check what wild creatures are doing, because very often they will surprise you. David Gremelet's story embodies something I heard again and again during my research for this book, how scientists went into the field expecting to study one thing and ended up studying something else, because conditions on the ground were so different from what they expected, different in terms of climate, but also different in terms of the lives and the activities of their subjects. The dovekies were able to pivot very quickly to a new food source because they have what scientists call plasticity, like that old comic book hero, Plastic Man, who could stretch his body into any shape at the drop of a hat. We all wish in biology that every species out there was like Plastic Man at this juncture, because plasticity in nature allows a quick response. And when conditions in nature are changing rapidly as they are now, it is a very handy trait indeed. And if there were an Olympics for plasticity, there is one creature that really stands out, because it changed not only its behavior, as we saw with the dovekies, changing their feeding habits quickly. This is a creature that is really almost like Plastic Man, changing its very lifestyle and even its body at the drop of a hat. This is the Humboldt squid, the plastic squid of the title of the book, Winnie. For example, people thought this squid had disappeared from its traditional fishing grounds in the Gulf of California. There are parts of the Gulf there where people have been fishing for these huge squid, the Humboldt squid, for decades. And after a series of marine heat waves, the squid were gone, and the fishers thought, well, that's it. The squid have moved off to find cooler waters. But in fact, when they went out and did surveys, they found that the squid were still there. In fact, just as plentiful or even more plentiful than they had been before the water warmed up. But what had happened is, instead of moving, the squid had transformed their lifestyles through the natural plasticity in their bodies. They had started to mature twice as fast. They switched their diet to something else. They began breeding in half the time it used to take them. And under those constraints, their bodies would grow only to a fraction of their former size. They were too small to bite on the hooks that the fishers had previously been using to catch them. And when they could occasionally hook one, they were throwing them back, thinking they were juveniles or even another species altogether. They thought they were gone, but they were still there through that natural adaptability. Now, most climate change responses that we've seen in nature to date are the result of plasticity, that built-in response that plants and animals are capable of. It varies among species. Everybody has a bit of it. We have a bit of it too. And one of the best ways to understand it is to consider the recent Olympic Games and Paralympic Games in Tokyo, when you had elite athletes from around the world descending upon Tokyo. Well, many of them descended literally upon Tokyo because they had been training at high altitudes. And if you go to high altitudes to train, you're training in a place where the air is less dense. So every breath that you take contains fewer molecules of oxygen. And when you first go to high altitudes, you're out of breath, but over the course of days, and if you train there, your body adjusts through its natural adaptability by producing more red blood cells, altering blood flow and breathing habits, so that you get enough oxygen to exercise at that altitude. So when you come back to sea level in Tokyo, you have a boost because your body is still used to less dense air. You start getting more oxygen to your muscles when you come back to dense air to compete. So that is plasticity, and that's most of what we have seen in nature. We're seeing all these incredible changes going on based on things that plants and animals can already do. But in certain situations, scientists have also begun to measure evolution in action, new traits evolving to cope with this atmospheric crisis. And one of the best examples comes to us from the Caribbean. It's another lizard. If you can stand another lizard story tonight, I want to give you the story of a lovely little Anole lizard, which is sort of a distant cousin to an iguana. If you can imagine a small iguana with a wonderful throat pouch that it likes to display with. It's a marvelous little creature. Many anoles in the world. There is a particular anole that lives in the Turks and Caicos Islands in the Caribbean that is very poorly known. has a limited range there. And a fellow named Colin Donahue had gone down to study the Anole lizards. He and his team went down and they measured all sorts of things about these. They caught them, measured them, weighed them, and released them back into the wild in preparation to study the effects of rats that had been feeding upon these lizards, non-native rats on the islands, which were due to be eradicated. They had this rat eradication project. So the idea of the study was you measure all these lizards and then they take the rats away and then you go back and see if the lizard population has some relief then from being fed upon by these Norway rats. So anyway, he did all that work and went back home to the lab, and then a hurricane struck. His research, as so many other scientists that I talked to, took a turn, an unexpected turn. So let's catch up then with the story of Colin's research from the Turks and Caicos, which is from chapter 8, and it also begins with a quotation. This is from Giuseppe Lampedusa's wonderful novel, if you haven't read it, The Leopard, where he wrote, "If we want things to stay as they are, things will have to change." Actually, it was 2 hurricanes, Donahue clarified when I called to ask him how the story played out. Hurricane Irma struck first, pummeling the eastern Caribbean with torrential rains, storm surge, and Category 5 winds exceeding 175 miles per hour. Just 2 weeks later, Hurricane Maria swept through with similar force. The combined storms devastated low-lying islands like the ones where Donahue's lizards lived, uprooting trees, flattening structures, and leaving both natural and human communities reeling. Needless to say, researchers put the rat project on an indefinite hold. But for Donahue, that setback also offered an opportunity. While his questions about lizards and rats would have to wait, he was now in the perfect position to study the effects of hurricanes. Had any lizards survived? If so, and if that surviving population was different from the one he just measured, then he might be able to document natural selection in action. We had no idea what to expect, he told me. We thought it was a long shot, but I knew we weren't going to get another chance at that kind of data. So he cobbled together some funding, headed back to the Caribbean, and found himself in a sort of scientific deja vu, repeating the exact same field project he'd just completed 6 weeks earlier. We were on a short timeline, so it was pretty much catching and measuring lizards all day long, Donahue recalled, but he described that activity with obvious pleasure, as if this were precisely how anyone would want to spend their time on a tropical island. In conversation, Donahue's enthusiasm for science borders on exuberance. He comes across as someone who probably keeps working and thinking long after other people might quit for the day and retire to the poolside bar. That may be why he recognized the potential value of returning so soon to resurvey his lizards. And it's almost certainly why it occurred to him to bring along a leaf blower. The customs officer was very confused, he said, and laughed out loud at the memory of trying to explain the science behind traveling with a large piece of landscaping equipment. We needed to know how the lizards behaved in hurricane-force wind, he told me. It was possible they might run for it or hunker down in the tree roots. We didn't know. And since watching lizards in a real hurricane was out of the question, Donahue used the leaf blower to simulate one inside his hotel room. And I've always wondered what the people in the next room thought about that. I mean, it's one thing if someone turns the TV on kind of loud, but a leaf blower. At any rate, Colin did this experiment, and what he saw when he turned on that leaf blower was how the lizards would scurry around to the backside of a stick and get in the lee, out of the wind, and they'd hold on. And then they'd increase the speed of the leaf blower. And they had a little measure so they knew how fast the wind was going, and they could get it up to hurricane force. And as it got stronger and stronger, the back legs on the lizard would start to flop off like this, and then the lizard would be holding on tight. And then the whole body of the lizard and the tail is flapping like a flag in the wind, and it's holding on for dear life. Until finally, let's go. And luckily they had a soft net right behind the stick. So they caught all the lizards safely and were able to return them to the wild. But when he saw that, it was an aha moment for the numbers they'd been seeing in their data. It explained the whole story. Because in fact, the post-hurricane lizard population was different. It was different. The surviving lizards had larger toe pads. and stronger front legs for holding on tight in the wind. And they also had shorter back legs, which had been the thing that was really mystifying to him until he saw the lizards flapping like a flag in the wind. And if you can reduce the drag, you'll hold on for a few minutes more, and that might be enough between survival and death. And so by doing this experiment so soon after the hurricane, they were able to isolate and measure survival of the fittest, natural selection happening, evolution in response to climate change playing out not over the course of centuries or thousands of years, but within a single field season. And they went back in subsequent seasons and learned that, in fact, those traits were being passed down to the next generations of lizards. And then they looked more broadly at the whole Caribbean and found that wherever you could find places where hurricanes were more frequent, the lizards in those populations would have those features as well. So they were able to document a change, an evolutionary change playing out in real time. Now, climate change biology is full of those sorts of surprises. And I hope that you will agree with me that there's a lot more to it than just a polar bear on an iceberg. Now, we've talked already about timing challenges. We have talked about extreme weather. We've talked about plasticity, even evolution. And I have to tell you, we haven't even scratched the surface on this topic. Consider movement, which in some ways is the most intuitive and most common reaction to a change in climate. Scientists have already measured over 30,000 range shifts in nature, where plants and animals are changing where they live to try to find in the landscape the temperatures and other conditions that they have evolved with. They estimate that between 25 and 85% of all species are probably moving at this time, which even at the low end of the estimate is a quarter of all the life on the planet. That is a massive perturbation, if you will, in biology. And it is challenging and upending all sorts of ecological relationships and processes, from predation to competition to hybridization to parasitism, and yes, even to extinction. The mouse-like bramble-key melomes, fuzzy little creature in Australia, recently became the first mammal to be confirmed lost to the climate crisis when all of its habitat was inundated by sea level rise, and the creature had no possibility of moving to a new location. And that's just the one that we've been able to measure. So studying this, studying climate change, does not necessarily make scientists worry less about the crisis, but it can help them to worry smart. It can help them to distinguish the creatures that are more resilient from those that are most at risk, and it can help them very vitally to allocate resources where they're needed most. I mean, precious resources, their research time, their conservation efforts, the policy changes that we must make need to be precise in this moment of triage. And to that, I would also add that as individuals, climate change biology can help us to allocate our emotional capital, which is also a limited resource. We need to know what to worry about, which creatures are most at risk. I would argue that at this time of crisis, which is indeed daunting, that climate change biology teaches us that this is a crisis that deserves our curiosity as well as our concern. And I've come to be a firm believer in the power of that curiosity to affect change. Talking with scientists working at the front lines around the world on these problems, you would think that these might be people who would have more cause than anyone to despair. Yet, I have found again and again how passionate they are for their work, how committed, and how they know that they are making a difference. Curiosity can help us all feel the same way. So in a moment, I would like to take questions, and I hope that you have some questions for me, but let me end first with a passage from the conclusion to the book, which also begins with a quotation, this time from the Bard, from Shakespeare's King John, who wrote, "Strong reasons make strong actions." I subscribe to a philosophy expressed to me by Gordon Orions, an eminent American biologist whose 7-decade career has spanned everything from blackbird behavior to the evolution of fear. When asked what a concerned citizen should do about climate change, his response was immediate and concise: everything you can. In that simple phrase, Orion's managed to capture both urgency and agency, the seriousness of the issue combined with the importance of taking action at a relevant scale. It's not a new idea. 19th century thinker Edward Everett Hale expressed something very similar in a verse conceived long before anyone was worried about their carbon footprint. "I cannot do everything, but still I can do something," he wrote. "And because I cannot do everything, I will not refuse to do the something that I can do." The value of the advice from both Orion's and Hale lies in their choice of the word can, a verb that is rooted in possibility and adaptable to any circumstance. It helps us focus our energy on tasks immediately at hand, tangible things like how we drive, shop, eat, travel, protest, vote, dry the laundry, or even cut the grass. Naysayers will claim that taking personal action is trivial, an empty gesture in the face of a problem so large. But that position is wrong. And it's not just slightly wrong, it is the opposite of the truth. In nature, we have seen how the responses of individual organisms determine the fates of populations, species, and entire ecological communities. The same pattern applies to society. Addressing climate change requires a fundamental cultural shift in our relationship with energy, from how we produce it to how much of it our lifestyles demand. That makes individual action more important, not less so, because it is the collective behaviors and attitudes of individuals that define and change a culture. Yes, we need stronger climate policies and strong leadership to carry them forward, but those things will be the results of cultural change, not the cause of it. Doing everything one can about climate change is also a fitting approach biologically, because it is precisely what plants and animals are doing. Their responses are playing out all around us every day, a constant thrumming call to action. Because in spite of the complexity of our societies and the technologies that we surround ourselves with, we're just one more species on a changing planet, facing the same climate challenges and drawing on the same basic toolbox of potential solutions, with one notable difference. Unlike any other organism on Earth, people have the ability to do more than simply react to climate change. If we so choose, we can alter the behaviors that are causing it to happen. Thank you all very much. I would be glad to take any questions you may have. Questions on?
Yes, I've asked folks on Zoom to enter their questions in the chat window. And if folks here have questions, if we could just repeat the question so that the folks on Zoom can hear it, that'd be super.
Good, yeah.
And no questions from Zoom so far.
Start.
You mentioned earlier the solubility of carbon dioxide in water, and I wonder if that's led you into any inquiry in ocean acidification.
Oh, what a great question. So the question is that because carbon dioxide is soluble in water, what's happening with acidification in the ocean? It's a marvelous question. I don't know if you ever spilled it, like in something on your shirt, like mustard at your grandmother's house when you were a kid. But if you did that at my grandmother's house, she would immediately go and get the soda water, plain carbonated water, and get the blot of mustard out. She was spot on, because when you dissolve carbon dioxide into water, you don't just get bubbles, you get carbonic acid. That water becomes slightly acidic. And what acids do is they break up the bonds that hold things together. And so they break up the bonds in mustard, in a shirt, but they will also break up the bonds that hold things together in the ocean. And one of the challenges that creates for ocean creatures is in building a shell. And this is work that actually began, some of the first observations of this challenge were right here in the Salish Sea and Puget Sound with commercial oyster growers who were having a hard time, in some cases, in some years, with the young oysters forming the first bit of shell. When they first form that shell, they're using a form of calcium carbonate called aragonite. which is a particularly fragile form and much more likely to erode. So it's very difficult for a young oyster to make its first shell in an acid ocean condition. And so that is a huge challenge for young oysters and for other creatures. And one of the creatures that they study is a little, it's called the sea butterfly, if you will. It's a little teeny snail. If you can imagine a snail with almost like wing-like feet. It's a beautiful, I mean, as far as zooplankton go, they're pretty cool. They look very beautiful. Sort of this glass-like shell that, you know, catches the light from your microscope and lights up. Anyway, enough about that. So the shell itself of this beautiful glass-like shell is made from aragonite. And unlike an oyster, which will, as it matures, switch to a tougher form of calcium carbonate, aragonite is all you're ever going to get if you're a sea butterfly. So you better figure out how to make a shell. And this has been a worry because in laboratory experiments, you can project future acid conditions of what your sea is going to be like. And you can make them acidic enough so that those poor sea butterflies, their whole shell will just erode. So they were very encouraged when they got to studying this in place. This work was done down in Antarctica. There are places underneath that sea ice that get really acid at certain times of year. So they said, well, let's see what the sea butterflies there are doing, and found in fact that some of them at least are able to repair their shells. So the shells are being damaged, but they're able from the inside to build these patches, if you will, like a thumb in the dike, if you will, that can be 4 times as thick as the original shell. So there is some ability to resist that erosion. Of course, that takes energy. And so it's, you know, up for grabs how that's going to affect sea butterflies long term. If they're spending all their energy repairing their shells all the time, they're not going to have as much energy to breed and do the other things that sea butterflies do. So it remains a big concern, particularly for young shellfish and for some of these creatures like sea butterflies that have fragile shells. And in addition to that, it impacts all sorts of things like how fish communicate, because, you know, sound travels differently through acidic water and so on and so forth. But shell building is one of the keys. Yeah. Bob.
So after all your research and reading and writing, what's your sense of the future? Your feeling of the future of the world? More pessimistic, more optimistic, somewhere in between?
Yeah, no, great question. So Bob's question is, what's, you know, after all of this work, you know, what are my feelings? And it's a mixture of things, of course, but I will say that I feel inspired by a couple of things. One, by some of the resilience that we see in nature, and how species, some at least, there are species like our Melomes going extinct, but there are others making these remarkable shifts and pivots in behavior, in lifestyle. And it occurs to me seeing that my God, you know, if a lizard can evolve larger toe pads to deal with this crisis, maybe, you know, we can change a few of our own habits, right? So I feel some inspiration from that. And I also feel an inspiration from these scientists, which I mentioned, that, you know, who are on the front lines and you would think would have more reason than any of us to feel despair and yet feel energized by what they're doing and feel that they're making a difference. And I feel that that curiosity then we can use as a very powerful tool in fighting this. I mean, it is really hard to solve a problem if you're not even interested in it. And curiosity is a path for us to know more and use that knowledge to act. Yes.
I'm going to ask about your polar bear friend, not that specific one, but polar bears in general.
Yeah.
What's happening with polar bear populations and distributions and overall health of their species?
So the question is, what about that polar bear, the poor thing on its iceberg? And there's not a simple answer to the polar bear question. They divide the polar bear population into subpopulations to try to get their heads around what's going on up there. And some of those subpopulations are indeed diminishing. Others seem to be stable. There are even a couple where the polar bears seem to be doing all right. And the theory is that it has to do with the changes going on up there and where they're taking place and the resources that the polar bears have at their disposal. So in places where the sea ice is shrinking fast and they're not getting enough to eat from the seals they traditionally fatten up upon, those bears are suffering. There is some plasticity behaviorally. Bears will go on shore and they will hunt other things. They're raiding seabird colonies and they're eating other beached whale carcasses and anything they can find. But it's not as good a source of protein and fat as the seals. So those populations are suffering. In other places, you also see some increase in productivity with the increases in temperature. So where there's still sea ice and maybe even more seals than before, you see bears increasing. So it's a combination. Too soon to say ultimately what will happen. Certain populations definitely diminishing, others, at least for the moment, more stable.
Sure. For someone like you who has such an abundance of curiosity, how do you decide what to focus on?
How to decide what to focus on. That is a really hard problem. Never try to go on a walk with me. If we won't get beyond the parking lot. No, it is a challenge. But for me, in terms of the projects that I work on, there's a difference between what is a good idea for a book and what is a book. And so I have to make sure that whatever passion of the moment has a narrative that will carry it through and enough information to fill out the story. Certainly with climate change biology, that was not an issue. There's so much information and so much going on. But I always will sit down before I start a project and do very detailed outlines and make sure that I really have a story to tell. Because some things are really cool and interesting, but they're only cool and interesting in the parking lot on your walk. You're not going to do a whole project of it. So yeah, but it is a challenge. It is a challenge to focus. Oh, yeah.
If any other questions, here's one.
Not to hog the questions, but I have one that I've been reading about off and on. CO2 is a concern and all this, but what about the big stereo and methane? That people say, well, the methane is going to burp and it's going to blow us all away, and it's 40 times more deadly and all this kind of stuff. Yeah. Can you address that?
Sure. Yeah. So the question is methane, which we talk about CO2 a lot, but there are other gases that are adding to this problem. And one of the nasty ones is methane, because it's much more potent, retains heat more than CO2. And there's no good news about methane, but if you really wanted to get good news about methane, the good news is that it breaks down a lot more quickly. CO2 will last in the atmosphere for hundreds of years, methane for only a couple of decades. Bad news is when it breaks down, one of the things it breaks down into is CO2. So it is a problem. There's not as much of it going out, but when you get it out there, it's potent. So we deal with it in many of the same ways we would deal with CO2. Reducing the amount that gets out that's conservation. Is the key to reducing what's going on up there. Limiting the amount of this stuff that gets out. And methane is one that, of course, that people are really worried about. It's a byproduct of a lot of petroleum extraction, and it's also, as you mentioned, there are places where it's trapped now, where it can burp out if we change conditions too much. And so, again, it's just something you want to keep that genie in the bottle as much as you can. Good question. Yeah.
I feel like that's a great segue for if you wanted to talk at all about positive feedback loops, because I think you've been a ton across methane. Like, is there, do you have any other positive feedback loops that we should be worried about besides like warming planet and methane coming out of the permafrost?
This is a really good question about what we call a positive feedback loop, where if something starts to change, that change makes the change happen even more quickly, right? And we see it in a lot of ways with climate change. When you, start to, melt the ice off of, the tundra, and then you expose darker ground that absorbs more heat and melts more ice, and and off you go. You're off to the races. And there are many feedback loops like that we see. So they're all a challenge because they accelerate the whole process. But I want to counter that with a positive feedback loop that we can, I think, use in our own lives that helps us to fight climate change. And this gets back to the idea of individual action and this idea of any one of us feeling so small against a problem that is so huge. And the analogy that I like to use about that circumstance is how you feel when you have a friend who is going through some kind of a bad patch. Maybe there's a there's been a death in the family, or there's an illness. There's some problem that you have a friend facing that you can't fix alone. You're not going to snap your fingers and make it go away, but you want to help. You want to help, and you think, well, what can I do? Maybe I can take them a meal, or I can cut the grass for them. I'm going to go run errands, so they don't have to worry about that. It's not going to solve that problem, but it does help, and they appreciate it. And the thing that gets us to the positive feedback loop is that when you help a friend in that situation, you feel better too, because you're glad you did something. And when you do something like that that makes you feel better, you want to do more of it, right? And I feel that is very true about the small steps we can take and the big steps we can take in our own lives about climate change. When you change those behaviors that are, darn well are emitting carbon, you feel a little better about that. And that positive feedback makes you want to do more of it. And the more all of us start on those small actions, whatever it is, you turn off the lights when you leave a room, you drive less, you drive, if you can do it, you drive electric, or what, all this, the way you shop, the way you eat, whatever those small things are, you feel a little better. And and that makes you do it more. And as we all start experiencing that positive feedback loop, that's when we start to see change. I was on a radio program just a couple of days ago, and the person on right before me talking about climate change had been talking about how this past summer, with the heat waves and with the flooding and with the hurricanes and the fires, that a sort of a tipping point may have been crossed in public perception of climate change, where suddenly what had seemed remote, a bear on an iceberg someplace, well, tough luck there, sorry, but now suddenly it's in people's lives. They're seeing this catastrophe play out in their own lives. And she felt that, from the polling data and so on, that shift was happening in the public. And she made the comparison that it hasn't happened yet at the policy level, but if it happens truly at the public level, that it will happen in policy in Washington, D.C. as well. There's a lag there. Another, science term, if you will. There's a lag between those two actions, but a connection. So again, that feedback feeding up to Washington. She made that observation, which I thought was really a good one. That people are starting to change, and once people start to change their attitudes, we'll drag them with us in Washington, D.C. Anything from the web?
Nothing from the web. Everyone has said they really enjoyed it.
Great. We have one more question from.
Yes, well, okay, we talked about polar bears. Now, how about humans? What are you seeing? Are you seeing anything? I haven't really read much about human migration patterns. If there's any climate refugees that hear about it, is that really actually accurate?
Yeah, so the question is, what about people? And what about how are we responding to this change? And there's a really interesting, there are many examples of what's going on, but one recent one that I think is really telling is if you look at the recent hurricane that slammed into New Orleans, right? And you think about the sort of reactions we've been talking about in nature. We're talking about adaptations. We're talking about creatures moving, right? And you look at New Orleans and you see those very things playing out in our own species, right? And that in New Orleans, for this hurricane, the seawall that they built, the new one, held back the storm surge and protected the city. That's adaptation, isn't it? It changed a behavior there with a technical innovation, a structure that held that water back. But water was held back from a population in New Orleans that is still over 20% smaller than it was before Hurricane Katrina, when tens of thousands of people moved away from New Orleans, never to return, deciding that it was unlivable. So in that one example, you can see the very things that we're studying in nature playing out in human populations: adaptation and movement in response to climate change. So again, we're using the same toolbox. Yes.
Speaking of humans, I had also read that there's some some scientists are studying physiological changes in humans to adapt to a higher temperature. So for example, like our core body temperature going up a few degrees so that we can adapt to higher temperatures. Also, our corneas getting thicker, that kind of thing to withstand. Do you know anything about that? kind of feeling?
Great question. So what about physiological changes within our species in response to climate change? I don't know the specific studies, but I can tell you that yes, it will certainly happen. In that we talked about how people respond with plasticity to change in altitude also applies to how people respond to change in temperature. And I will quote my father, who is with us here this evening in the front row, the Hanson Family Peanut Gallery, who told me when I was graduating from high school and decided to leave the Northwest for Southern California to go to college. And he said, it's going to thin your blood living down there in that California heat, right? Well, technically not thinner blood, but he was spot on that I would have physiological changes to adapt to that hotter environment. Changes in blood flow, changes in the diameters of, blood vessels, how things move to the skin, and changes in behavior. Getting rid of the sweater, t-shirt, shorts, and some physiological changes, and that California sunshine was fine for 4 years, no problem. But really, those kinds of changes are built in, and those will be happening. There's also a marvelous study just published within the past, too late for the book, rats. A marvelous study looking at those sorts of changes over time in a range of species. And one of the greatest examples they came up with that I love was the Mulgo parrot from Australia. And they have, of course, museum specimens of these parrots dating back into the mid-19th century. And when they started looking at those parrots with that very question in mind, are there physiological changes that would be a response to modern climate change? They learned that, in fact, the bills of those parrots are 10%, up to 10% larger now than they were in the 1870s. And if you look at a bird, I don't know if you've ever thought of it this way, but you are looking at a performance athlete wearing a sleeping bag. The physical activity of flying through the air is intense and creates all of this body heat, and they are covered with down. How do they stay cool? They have a very few places on their bodies that are capable of dispelling heat. Some of it they do through the way they breathe and how they have these fabulous lungs and so forth. But also they must, get rid of heat through something like a bill, which has no feathers on it. And so if you need a larger, what they call in biology, a heat window, if things are getting hotter over time, you expect the bills to grow. And in fact, the bills of those parrots and many other species of birds are growing in response to this climate. So I don't know, what that will mean for us, but certainly our bodies will adapt to this situation as well. Marvelous question.